Welcome. Let's talk about double interpolation, shall we? So, to do that, I'll use the following example to illustrate what double interpolation is all about. So, let's talk about double interpolation. All right, cool. So, in this problem, we're given the following. We're given a regenerative Rankine cycle with two feed water heaters. One is a closed type and one is an open type. Now steam enters the turbine at 10 megapascal at that temperature, and it exits the turbine to the condenser at the pressure of 11 kPa. Well, some steam is also extracted from the turbine at 1.3 megapascal. This goes to the closed feed water heater. Then we have 0.7 that goes to the open feed water heater. Alright, the feed water heater is heated to the condensation temperature of the extracted steam. Now this is in the closed feed water heater. The extracted steam leaves the closed feed water heater as a saturated liquid. Now that one is crucial. So it leaves the closed feed water heater as saturated liquid. Alright, and then it's throttled to the open feed water heater. Show the cycle on TS diagram. Okay, we'll do this as a bonus. And then mass flow rate is to be determined given this as our net power output and the thermal efficiency. So the purpose of this video is to show you how to double interpolate, or we'll learn how to do double interpolation, and we'll use this very example to show that. So let's go ahead and draw a TS diagram of this whole plant. It's a regenerative Rankine cycle, and the schematic is as follows. That is the schematic. So let's go ahead and do that. Okay, from the data we are given, that steam enters the turbine at 10 megapascal. So at that point it's 10 megapascal, and what else? Steam is exhausted to the condenser at 11 kPa. So at state 11 the pressure is 11 kPa. That's cool. That's a nice one. Okay, so we have 10 megapascal, and then we have a condenser pressure of 11 kPa. What else? Let's change this to red. Alright, and the temperature is it enters the turbine. This is the same as pressure at 600 degrees Celsius as it's given there. Cool. Alright, so first things first, let's go ahead and just indicate our axis of the TS diagram. So we'll have vertical axis, and then we'll have horizontal axis. Okay. Now on the vertical axis, we'll plot the temperature, and on the horizontal axis, we'll plot entropy. And as usual, I'll indicate the saturation dome, and our whole plant operates between the maximum pressure is 10 megapascal and the lowest pressure is 11 kPa. So I'll just go ahead and indicate that on TS diagram. Now constant pressure lines look like this on a TS diagram. So that's a constant pressure line. So all throughout this line, all throughout that line, the pressure is 10 megapascal. Okay, cool. So this is the boiler pressure line of 10 megapascal, and the lowest pressure at which this plant operates is the condenser pressure at 11 kPa. So I'll indicate that as well. I'm just indicating the pressure lines. That's all that I'm doing. All right. Cool. So this is the condenser pressure. I can call it PC, denoting condenser at 11 kPa. All right. What else are we told? Okay. We are told from the problem statement that we have an extraction of steam at 1.3 megapascal and also at 0.7, 1.3 to the closed feed water heater and 0.7, excuse me, to the open feed water heater, as it can be seen there on the schematic. So this also helps with drawing. All right, cool. So we have this pressure down. Now we'll indicate this pressure and that. So between 1.3 and 0.7, which pressure is greater? Can already see that 1.3 is greater, so I'll indicate that. So indicate 1.3. So that's a constant 1.3 megapascal pressure line. You can say here maybe closed feed water heater, 1.3 megapascal, and change this to different color. And the last one is 0.7 megapascal. Okay, so this is open feed water heater at 0.7 megapascal. Okay, cool. That's nice. So I have these lines drawn. Now what? Well, I know that the process that I'm looking at is a regenerative Rankine cycle. And in a Rankine cycle, we have components. We have a turbine, a boiler, condenser, and we have pumps. In this case, we also have open feed water heater and a closed feed water heater and a throttle valve. All right. So let's indicate our states, shall we? And indicate these components. Okay. So we are told that steam enters the turbine at 10 megapascal. There it is. Enters the turbine at 10 megapascal. So 10 megapascal. This is 10 megapascal. So it should be somewhere along this line. Somewhere along this constant pressure line. So steam at 10 megapascal will be somewhere right here, somewhere there in the superheated region. It's steam. Okay, so I cannot indicate it here because that will be saturated vapor. Okay, all right, so that's our point at. All right, knowing that it's a turbine, the question statement doesn't say anything about losses. Therefore, I'll assume that this is an ideal case, an ideal operating turbine with no losses, and I know that it's an isentropic process. So I'll draw a vertical line to indicate expansion in the turbine from pressure 8 to pressure 11. Okay, so that will go like that. Okay, so now, okay, let me just make sure, the drawing looks nice. So yes, so I'll indicate here so that looks somewhat yeah, okay. I think not. All right, I need to change how my dome looks like because yeah, it's too wide. So let me see if I can do something about that. Okay. All right. All right, cool. I think this is much better. Okay, so that's it. This is 11. And this will be the direction of steam flow. And from here, we see that at 9, there's extraction of steam to the closed feed water heater. That will be 9 there. We'll have extraction at 9. Yeah, extraction at 9. We'll also have extraction to the open feed water heater at stat 10 or at point 10. Okay. And all throughout this direction still will be flowing. Yeah. Okay. Cool. So from state 11, from 11, steam exits the condenser and it enters pump 1. So it exits the condenser as saturated liquid at state 1, and then it goes through pump 1, and a pump is designed to pump, well, a fluid in a single state. In this case, it will be saturated liquid. So it goes through an isentropic process in the pump, and a pump can only pump saturated liquid. So that's why it has to be saturated liquid. So looking at this pump, pumping from state 1 to state 2. So the pressure is increased from the condenser pressure to the open feed water pressure. So we'll move from the condenser pressure to the open feed water pressure. This is the open feed water pressure line. So we'll move there. So since it's an isentropic process, we have no losses, so I'll just indicate it as a straight line. So that will be step 2. Step 2. Alright. Now what happens in step 2? In an open feed water heater, we have mixing that takes place. Extracted steam from the turbine mixes with water that's entering at step 2, and they all come out of the feed water heater as saturated liquid. Now we are seeing another pump there. So a pump can only increase the pressure of a saturated liquid. I should rephrase that. Alright. Seeing that it is a pump, pumps are designed to only pump fluids that saturated liquid, that are of one phase. So it cannot be a mixture. So it has to be saturated liquid. So whenever you say a pump, think saturated liquid. Yes, in this case. Okay, so this will be state 3. From state 3 goes to state 4. Now, looking at state 4, one would think, there we go, it's the closed feed water heater pressure, but no. Look at this, in a closed feed water heater, there is no mixing. Therefore, this pump can only increase the pressure to that of the boiler pressure. Alright, so this will move all the way from state 3. State 4 will be at the boiler pressure. although it will be at a lower temperature than state 5. Okay, cool. So we'll indicate state 5 there. State 5 will be at a slightly greater temperature than state 4. All right. Okay, what else? So we've indicated that. Now about state 6. What do we know? We know from the problem statement that the liquid where is that? Here it is. The feed water is heated to the condensation temperature of the steam. Okay, so as it leaves at state 5, it leaves at the temperature, at the condensation temperature of the steam extracted from 9. Cool. Condensation temperature of the steam. So condensation temperature of steam will be the temperature at state 6. And what else? The extracted steam leaves the closed feed water heater as a saturated liquid. Okay, cool. So it leaves as a saturated liquid at state 6. That's when it's leaving, so that's saturated liquid. That's why state 6 is exactly on the saturated liquid line. All right. So this is how, I guess in this video, we looked at how to draw the TS diagram of this problem. It was supposed to be a video about how to double interpolate, but it turned out to be a video of how to draw TS diagram. That is still fine. Alright, now all we have to do is to indicate what is this? I need to indicate how much, or what is the quantity of steam in each state or between each process. Okay, from 5 to 8, we know that that's the total quantity of steam, so we'll denote that by 1 meaning 100% full steam, complete steam. So that is 1. So that is 1, and between 8 and 9, we are still talking about 1, and it's only after 9, well, at 9, there is extraction of a certain portion of steam that is known as Y. So Y is extracted. Therefore, from 1 we had 1, and from that 1 Y was extracted, so we are left with 1 minus Y steam. 1 minus Y steam. Alright, now from 1 minus Y steam, Z, a portion of Z was extracted. Therefore, okay, so Z was extracted there, and what is now remaining from 1 minus Y? Well, we have 1 minus Y, and we extracted Z from that portion. Then we are left with 1 minus Y, and that will be the remaining steam, or the remaining portion will be what will flow this is what will flow or be exhausted to the condenser, and from the condenser it will still be the same through state 2, and then in the open feed water heater, Z will mix with 1 minus Y minus Z with the Y from 9. They'll all mix there. So if they're all mixing in here, at state 3, they're leaving as 1. 1 again is leaving. There's no mixing in the closed feed water heater, so 1 will leave like that. So that is 1. Alright. Cool. So we have 1 minus Y minus Z, and from 1 to 2 it's still the same, and at step 3 we have Z coming into step 3. Also at step 3 they're all leaving as 1 because it's step 3, it's after mixing in the open feed water heater. There's mixing that takes place. And one final process is from 6 to 7, which is a constant enthalpy process. You can just indicate that entropy is not conserved. If anything, entropy increases. However, what we do know is that H6 is equals to H7. So that's how you draw a TS diagram. The units for entropy is kilojoules per kilogram Kelvin, and we can have our temperature in Kelvin as well. So the video should have been about double interpolation, but if you could not draw this, if you wanted to learn how to do this, then this was your video, and it's been, well, yeah, God bless you and keep you safe, Come back for the next video where we do double interpolation. God bless you and keep you safe.